Hello everyone, I'm Ruidong from Peking University. I'm glad to share our work, dLoRA, Dynamically Orchestrating Requests and Adapters for LoRA LLM Serving. This is a joint work of Peking University and Shanghai AI Lab. And the first author, Bingyang, was unable to come and present due to visa issues, so I will present this paper. With the development of large language models, numerous software applications are leveraging these models to provide better services, such as ChatGPT for chat applications, Perplexity for search engines, and GitHub Copilot for code completion tools. The large language models behind these applications all follow a unified inference service paradigm known as autoregressive generation. This generation process involves multiple iterations. In each iteration, the input token passes through the entire large language model to predict the next output token. The output result then serves as the input for the next iteration. This process continues until the end of sequence token is generated. Due to various customization needs, many users require fine-tuning large language models using targeted and labeled datasets. Low-rank adaptation, LoRA, is one of the most popular parameter-efficient fine-tuning methods. Specifically, for each pre-trained dense weight that needs fine-tuning, LoRA keeps its parameter frozen and additionally trains two low-rank metrics A and B. Since metrics A and B are small, the memory usage can be significantly reduced, and the computation can also be decreased, while the model quality is similar to full fine-tuning. For example, compared to fully fine-tuning GPT-3 with 175 billion parameters, LoRA can reduce the number of trainable parameters by 10,000 times and the GPU consumptions by 3 times while achieving comparable model quality. Additionally, during the inference stage of large language models, LoRA also has its unique advantages. Although the adapter's parameters are trained separately from the pre-trained weights during the fine-tuning stage, each pair of low-rank metrics, A and B, can be multiplied and merged with the pre-trained weights before the model is deployed. In this way, serving a LoRA LLM during inference does not introduce any additional computational overhead. However, since the parameters of proprietary large language models are not publicly available, or the customers want to avoid the hassle of deployment, the pre-trained large language models and various fine-tuned LoRA adapters catering to different customers or scenarios are often managed centrally by the cloud platform. Faced with the various types of user requests, the cloud platform needs to serve large language models with multiple LoRA adapters simultaneously. So the question is, how to serve multiple LoRA LLMs? We found that previous related solutions cannot perfectly solve this problem. Earlier frameworks for large language model inference primarily focus on efficiently serving a single large language model without addressing how to effectively serve multiple LoRA LLMs. On the other hand, previous model serving orchestration mechanisms mainly focus on the orchestration and scheduling of traditional deep learning models, overlooking the unique characteristics of LoRA and LLMs. Furthermore, we discovered that even combining these two approaches still leads to inefficiencies at both the replica and cluster levels. First, at the replica level, if using the merged inference as the original LoRA paper suggests, where the pre-trained weights are combined with the LoRA adapter, it will cause each iteration to serve only one type of request. When the cloud platform needs to handle multiple types of requests simultaneously, merged inference results in other requests having to wait, and thereby increasing the queuing delay. For example, as shown in the right illustration, when 3 requests belonging to 2 different types arrive, the processing time for these requests is twice as long as serving 3 requests of the same type, and the GPU utilization can only reach 50% of the ideal situation. Second, at the cluster level, the burst of variable requests leads to severe load imbalance across replicas under static LoRa placement. For example, when we deploy 8 model replicas and evenly distribute the LoRa adapters across different replicas, we observe significant load imbalance among the replicas. This occurs because during short-term bursts, different requests require variable iteration rounds, and the distribution of different types of requests is also skewed. Consequently, some replicas experience long queuing delays, while others have relatively short delays. In this context, our key insight is that we should consider the dynamic characteristics of requests, the real-time placement of LoRa adapters, and their interdependencies for dynamic orchestration and scheduling. Based on this insight, we developed dLoRA. dLoRA is an inference serving system that serves multiple LoRa LLMs in a cluster. Within a replica, dLoRA employs a novel cross-adapter batching technique to process requests to different LoRa adapters in a single batch, thereby improving the GPU utilization. Across replicas, dLoRA dynamically migrates LoRa adapters and requests within the cluster to achieve better load balancing. This figure shows the overall architecture of dLoRA. First, at the replica level, we introduce a new LoRa inference method called unmerged inference. The core idea is not to merge the LoRa adapter into the pre-trained weights. This allows different types of requests to be batched together for the pre-trained weights computation, while parallelly executing the LoRa computations corresponding to their respective LoRa adapters. This approach reduces queuing delay and improves GPU utilizations with larger batch size. However, this method introduces additional computational overhead, thereby affecting the end-to-end latency. According to our tests, the computation time for the LoRa adapter can reach up to 40% of that of the pre-trained weight. This is because each pre-trained weight introduces 2 additional matrix multiplications and 1 matrix addition. As previously mentioned, we highlight how unmerged inference incurs additional computational overhead, while merged inference leads to significant queuing delays and low GPU efficiency. Therefore, one of our key insights is why not use both merged inference and unmerged inference? A combined approach of these 2 batching methods can potentially offer a more balanced trade-off between queuing delay and computational overhead. However, implementing a dynamic switching scheduling algorithm is not simple. Firstly, the overhead of switching is unnegligible, as it requires additional matrix multiplications and additions or substitutions, since the decoding iteration time is typically only a few milliseconds. The overhead itself could even exceed the decoding iteration time. On the other hand, if complex scheduling is done at the iteration granularity, the fast iteration speed adds further complexity to the scheduling algorithm. To address this problem, we propose a dynamic cross-adapter batching technique. Based on the request arrival pattern and current state, dLoRA dynamically switches between merged and unmerged inference with different batching strategies to reduce the end-to-end latency. To decide an appropriate switching time without frequent switching, dLoRA dynamically adjusts the switching threshold with threshold tuning according to the request pattern. dLoRA also adopts a credit-based batch generator to generate potentially efficient batching plans without the starvation of requests. A final decision is made by taking all factors into account, including execution time, queuing delay, and switching overhead. Please refer to our paper for more details. To address the load imbalance issue among replicas, we first propose a proactive dispatching technique. In cluster scheduling, beyond the execution time of requests, several other factors also impact the end-to-end latency. For instance, if a request is dispatched to a replica without a corresponding LoRa adapter in GPU, the LoRa adapter loading time must be considered. On the other hand, if it is dispatched to a heavily loaded replica, there will be queuing time as well. Therefore, compared to a simple round-robin dispatching approach, proactive dispatching considers both the potential adapter loading time and queuing delay to balance the load across replicas. However, even when considering these factors during dispatching, load imbalance among replicas can still occur. In the short term, due to the varying iteration rounds required by different requests and the difficulty of perfectly predicting them, some replicas might have requests executing quickly, resulting in a lighter load, while others might be heavily loaded. To address this issue, our key insight is the need to reactively migrate workloads based on the real-time load conditions to balance the load. Unlike ordinary load balancing, in the LoRa scenario, we must consider both the LoRa adapters and requests, as well as their interdependencies. To tackle this problem, we propose a reactive request adapter co-migration algorithm, modeling the migration problem as an integer linear programming problem, ILP, with certain optimizations. This enables dynamic migration between replicas. And please refer to the paper for more details. In our experimental setup, we conducted large-scale experiments using 4 nodes, each with 8 NVIDIA A800 GPUs, testing the performance of 128 LoRa adapters while serving Llama 2 models of various sizes. The workload was selected from the ShareGPT dataset of human-machine conversation. Since there was no available request arrival pattern at the submission time, we used the Microsoft Azure trace to generate it. The trace is also commonly adopted in previous works. For our baseline, we selected the state-of-the-art solutions at the submission time, vLLM and HugginFace PEFT. We first conducted large-scale end-to-end experiments. The results show that under various models and loads, dLoRa improves the throughput by up to 57.9 times compared to vLLM and up to 26 times compared to PEFT under the SLO requirement. Subsequently, we conducted an ablation study to investigate the effectiveness of each technique. Firstly, within a replica, compared to merged inference and unmerged inference, dLoRa better balances the trade-off between computational overhead and queuing delay. Under varying levels of skewness in request distribution, it consistently achieves superior performance. Secondly, for the cross-adapter load balancing strategy, considering the placement of LoRa adapters and the load conditions of different replicas, proactive dispatching achieves better inference performance. Reactive migration further enhances load balancing. Ultimately, dLoRa outperforms round-robin by 3.6 times and proactive dispatching by 1.4 times under the SLO requirement. To conclude, we propose an efficient serving system for multi-LoRa LLMs, dLoRA, which dynamically orchestrates LoRa adapters and requests simultaneously. Within each replica, dLoRA dynamically merges and unmerges adapters and accordingly batches requests to reduce the end-to-end latency. Among multiple replicas, dLoRA dynamically migrates both requests and adapters to balance the load. And the evaluation shows that compared to the state-of-the-art solutions, dLoRA achieves significant throughput improvement under the SLO constraints. Thanks for listening. I'm glad to take questions.